before this thought experiment and these theorems, interpretations like QBism and relational quantum mechanics had some story of the form Wigner and Friend give different accounts of what's happening in the experiment because different things happen to them, or they know different things about what's going on. And that sounds like a okay, satisfying story until this theorem really forces you to mean, but what do you mean by this they describe in different ways? Like, what is, in your interpretation, what is happening really in the world? Like, does he actually see something and Wigner is just ignorant? Yeah, it's been a headache trying to figure out this, and it's fantastic actually to think about this because we had this story for many years, and now we have a concrete result that really forces us to sharpen our intuitions. What is an observer? What does it mean for something to happen relative to an observer in a superposition? So it drags like relational quantum mechanics, QBism, even neo-Copenhagen interpretations. There's like this idea like quantum mechanics doesn't need an interpretation because it's about data, about the real world. These interpretations now are forced to kind of talk about this. We are really like confronted with making concrete choices of what it means for these things to happen.
Hello, welcome back to the Quantum Foundations podcast. I'm Maria Violares. I just finishing up my PhD in Quantum Foundations at the University of Oxford. And today I'm joined by Andrea Di Biagio, who is a postdoctoral researcher here at IQOQI Vienna. And this is the mathematical installment of the podcast where it's aimed at people that have had some introduction to quantum mechanics and are familiar with the mathematical formalism. And we're going to explain some aspects of the foundations of quantum mechanics in technical detail. And in particular, the focus of our episode today is on extended Wigner's friend thought experiments and what they tell us about reality. So thank you, Andrea, for joining us.
Yeah, thanks for having me.
And hope you enjoy this episode. So we've said we're going to talk about what extended Wigner's friend thought experiments tell us about reality. And maybe a good place to start is saying what a Wigner's friend thought experiment is.
Right, okay, good. Let's get into it right away now. The Wigner's friend thought experiment is, I would say, it's like the double-slit experiment is one of the main intuition pumps of really digging deep into what's weird about quantum mechanics. And the double-slit experiment is about interference and not being able to think that there is one thing that happened or the other one. And Wigner's friend is very similar, but now instead of having just a particle, we have a person that has this problem. So, and it makes everything a bit more dramatic. And he also puts into question the ideas of what it means to be an observer. Right? In quantum mechanics, we have this kind of primitive notion of an observer. So this is a thought experiment due to Wigner, of course. That's why it's called Wigner's friend. And Wigner's friend is a person in a lab that is actually a quantum experimentalist that has a device, a measurement device. And he's going to perform an experiment, let's say measuring a qubit in the Z basis. But the qubit is prepared in a complementary basis, and so the outcome is uncertain, right? So the friend will do the measurement and he will get 0 or 1 as an outcome. So far so good. We know how to compute the probabilities. The friend would expect to see what happens if he does many measurements. Everything is good. The twist around this very basic scenario is that you imagine, instead of imagining this situation, you imagine being Wigner that is standing outside the lab. And in the original formulation, Wigner is just outside the lab thinking about what his friend is doing, right? And the main thing is that even though the friend is this huge complicated object, in principle, it could be assigned a quantum state, right? And in principle, you could apply unitary evolution to the friend, what's happening in the box, and you will get that the friend ends up in a superposition of having seen either outcomes, by the principle of linearity. Both if the qubit had been prepared in the 0 eigenstate, then friend would see 0, and this is what it is. But since it was prepared in a complementary, say the 0 plus 1 state, then this is the state that Wigner would assign to his friend at the end of the experiment.
And this is representing the qubit state
Right.
that
So
the
this
friend
would
measures.
this would be the qubit, and this would be
Okay.
the friend, the friend hyperspace.
Yeah.
And of course, this is a cop-out, but it's like some huge complicated thing. But somehow, even if you don't imagine having full knowledge about the state, still there was a state before, and that state would evolve into a friend having seen 0 if it was 0, and it would evolve into a friend having seen 1 if it was 1. But it was neither, and so you get superposition, and there's a superposition of 0 and 1. Okay. And the thing is, what's going on here is that Wigner's motivations don't matter too much when introducing this, but I think the main thing for us here is that there is a discrepancy between the description that Friend has of the experiment, where there is collapse because there's an update given by the measurement result, and the perspective that Wigner has, where since he's not interacting with the thing, and without assuming, say that one could assume that observers always collapse the wave function, but if one doesn't take that as a primitive idea, then in principle Wigner could choose to model what's going on in here using a unitary evolution, and in that case Wigner would assign an entangled state between the friend and the qubit. And so you have this mismatch between the two perspectives.
Right. So that's the problem with Wigner's friend. And what would you say Wigner's friend kind of tells us about reality, or makes us think about regarding what quantum physics tells us about reality?
Yeah, good. I think the main thing is it forces us to ask, when does a measurement happen? What does it mean? So I think in general this is one of the questions of the interpretation of quantum mechanics, is like, what is a measurement? What is an observer? When does something definite happen? I mean, people used to call it the collapse of the wave function, but in general, like when does a quantum state where there represents different possibilities actually becomes one of the possibilities, right? And normally we assume that, okay, because more or less we agree on what is classical and what is not classical, there are certain pieces of the word that are, classical, and they collapse with functions somehow. But here, and I will come to this later in the extended version of the experiment, here we imagine that somehow you can increase the control that Wigner has on the friend, so that you don't get this decoherence or like amplification, like loss of information that normally is like a science of classicality, because Wigner in principle could still like perform an interference experiment on the friend.
Yeah. So because Wigner's friend is making a measurement, but relative to Wigner, the friend is a quantum system, then it forces us to explain what's happening in terms of whether doing a measurement makes you a classical system somehow, or whether you're still a quantum system.
Right.
It forces us to have to answer this question.
Yeah, to think about all of these questions. Like if we decide that, okay, actually people always collapse with functions, then there is no Wigner's friend paradox, right? But this is a prediction of a failure of quantum mechanics in a certain sense, because why would it, when does it stop? Like, is it like a little light? Is it like a bacteria? Is it a mouse? Like, where does the collapse? What is the system that's big enough that cannot be put in a superposition? We don't know that. We've been trying to put things bigger and bigger in superpositions, and we can do it. It's really hard. We understand the decoherence that makes it hard, but it's not a fundamental property of quantum mechanics. It's a property of the setup and the control we have on the systems. And so, if quantum mechanics doesn't break, then we have this situation where we have two different descriptions, and then we can do this really funky stuff. For example, we could think about maybe friend can send a signal out from the lab and say, hey, I saw a definite result. And this can come out without spoiling the entanglement. So friend can just send a piece of paper out. This I think was Deutsch that came up with this, right? They can send a piece of paper out saying that, I've seen something, a definite outcome. But Wigner is out here and he still sees the thing in superposition, right? But then also he knows that his friend has seen something because he's been told, right? Or the other way around, Wigner could do an interference experiment on his friend, if this is the correct description, and then tell friend, hey, I did an interference experiment on you, you're in a superposition, and friend would be in the box, be like, what? Like, I've seen zero. Or what? Well, or what does he see? Does he see something? So there's all these questions that come up,
Yeah, cool. So that's Wigner's friend, and then the extension of Wigner's friend that we're going to talk about kind of combines this with Bell inequalities, and we're celebrating these 60 years of Bell's theorem right now as well, so it's a kind of relevant idea to discuss. So maybe now we can discuss Bell inequalities and what they tell us, and then we'll kind of merge these ideas together.
Yes, that's great. Before we move on, I want to make the difference. So what all these things we discussed are within quantum theory, right? These are like what the things quantum theories would tell us.
Right.
And the fantastic thing about Bell's inequalities, Bell's theorem is a theorem that's not about quantum mechanics. It's a theorem about all possible theories. And extended Wigner's friend scenario, so including arguments, Bell-style arguments in this thing, allows us to push these concepts of when does something happen and all these things beyond just the discussion within quantum mechanics, but also like a broader kind of space of possible theories kind of idea. So that's very cool. So
so that's quite an important intrinsic difference between this type of thought experiment, which is within quantum mechanics, and the Bell's theorem type of thought experiment, which is this kind of theory-independent one.
Exactly. Okay, so let's get into it. Bell's theorem. So let's make a drawing of an experimental setup. So you have a source of entangled photons, and the photons, they go into two different distant labs, where there is some machine that does a measurement of the polarization, say, and the measurement can happen on two different possible settings. So we call on this side, we call it X, and on this side we call it Y, the measurement setting. And it will have an outcome, and on this side we'll call it A, and on this side we'll call it B. All right. And you repeat this experiment many times with many pairs of photons, and each time the settings are varied independently from each other, and you record the measurements, outcomes. So it's a bad setup. And the question is, what kind of correlations can you expect between the measurements on this side and on this side? And let's draw instead of like a picture in physical space, let's draw like a causal diagram. So we have a variable A and a variable B, and this can be influenced by the measurement choice on each side of the lab, and they can also be influenced by this apparatus that is in the past, in the common past, which we'll just give it a name for now. Lambda. Okay. And I will argue this is like this is a causal diagram, then this will be understood. So in the sense that the arrows represent causal relationships, so what can be influenced by what.
Right.
And the reason that there is no arrow between X and B is because you can, in principle, arrange the experiment where this thing happens at a space-like separation from this thing. And so there should be no way for the measurement setting that happens over here on this side of the lab to influence the outcome on this other side of the lab. And vice versa, of course. And the reason why there is no arrow between these two things, or between these two things and another thing, is that we assume that it is possible in principle to arrange the experiment such that these two things are uncorrelated from each other, and also uncorrelated from whatever is happening at the source. And one can question these assumptions, but these are, it's the kind of assumptions that you would naturally come if you were to explain this experiment to somebody. They'd be like, okay, this is kind of what can influence what.
Right. Yeah.
Especially if they know special relativity. But even if they don't know special relativity, you still don't expect this to be influencing over here somehow, because they're happening in different spots. But let's say the reason why we believe that there is no connection from here to here is because of relativity. Right.
So in order to be consistent with special relativity, there's ways in which we could set up this experiment that it would have to have this causal diagram.
And in fact, the experiment has been done like this by Alan Space some time ago. Took a lot, huge pains to make them the two things happen in space-like separated regions, and make the choice, rotate the polarizers to make the different measurements, in the time of flight of the photons. It was quite a lot of stuff, I imagine. Right. So far we assume that X and B and Y and A are space-like separated. We assume that there is no meaningful correlations between X, Y, and the source. These are two assumptions of causality, let's say. And then, now say that we don't know anything about quantum mechanics, and we just think, okay, there is a common cause here that creates the correlations. We would write something like the probability of A and B given X and Y can be written as a set of marginals where P of A depends only on X and this common cause. P of B depends only on Y and the common cause. Will I get out of the thing? No, we're good. And then we have the probability of the common cause itself taking some specific set of value. And we're summing over all possible values of this thing.
Okay, could we review this equation again?
Yes, sure.
So this is probability of...
the probabilities of A and B taking specific values, given the values of X and Y, which are the settings. So given the orientation of my polarizers, what are the probabilities of getting some outcomes? Just a general shape of it.
Yeah,
I think.
yeah.
And
like the probability of getting 0, 1 when I've prepared
measuring on the vertical polarization or the oriented like this.
Yeah, yeah.
Right. So X and Y is like the polarizing beam splitter is like either like this or like this, and similar on this side for B. But we're abstracting away from the details of the experiment, and we're looking at what if we have this kind of causal structure. What kind of correlations can A and B have?
Yeah.
In general, so this could be like now here there were like measurements of polarizations, but this could be just some random variable that can take n values, and same for B and X and Y, all these things.
Right. Yeah.
And if we want to explain how these things come about using a causal structure, then like general principles of causal reasoning that we use in science in general, like it's called classical causal reasoning, we call it now. Have a procedure to assign to a kind of causal structure a family of probability distributions.
Right.
Where the only restriction on this probability distribution is that it has to be written in this form.
Right. Okay.
Right. That is a sum over values of lambda with this unseen variable, because we can assume that the correlations are explained by something happening in the apparatus.
Right.
So is this like value of lambda? It can be anything. It's just abstractly a member of a set. Right, it's the most general possible thing that you can imagine.
Yeah.
And the values, like the shape of these probabilities, is not determined by anything. It just needs to be a well-posed probability distribution for A and a well-posed probability distribution for B.
Right. And what happens if there is no kind of cause here? What would the equation look like?
If there was no cause, so if there was only one value that this can take, for example, then we would have just this, where there are no correlations between A and B.
Right, so they're fully uncorrelated.
Yeah.
But then if probability of lambda is like anything other than 1, then there is correlations that are kind of explained by this.
Yeah,
cause.
I mean, one thing that we need to take into account is that, I mean, this is just a subtlety maybe, but classical variables can only be correlated if they're a bit random. Like, if A is always 1 and B is always 1, in classical information theory that doesn't count as a correlation, because the correlation is the thing minus the average, it's like the variance kind of thing. Yeah. So, so these things could be that A and B are always 1, say, and it would be correlated. Yeah. But, if you want to explain more complicated things where A and B can be random, then it's harder to explain the correlation.
Right, yeah.
In particular, in a Bell experiment, A is actually totally random. If you just look at A, is always like 50-50 possibility of being 0 or 1 in a Bell experiment. Yeah. It's what's special about it that it's random, but it's correlated with a thing that's far away. Yeah. Right. And it's totally fine for things to look random and be correlated. You know, like in the EPR paradox, like you can explain kind of EPR correlations with a model like this, where like say that every day for some reason I send you a glove, you open the glove and you see it's a left-handed glove, I have the right-handed glove, and vice versa. So you don't know any day you don't know which glove you're getting, but you know that it's going to be correlated with the other one. Yeah. There's nothing weird there. Yeah. What's weird that we have in quantum mechanics is that we kind of expect things are fundamentally random, but they also know about each other, and that's kind of a tension. Somehow we get more correlations than they should. Somehow that's kind of intuition. This is what Bell's theorem points to. So coming back to our causal structure, so if you wanted to explain correlations between the measurements of A and B via a classical causal model of this form, we get a space of possible probability distributions, and this thing satisfies some constraints. Like you cannot have any probability distribution, any correlations you want, because this form constricts what they have. And the Bell inequalities are precisely one of these constraints. And in particular, there's many different kinds of Bell inequalities. The one we use often is the CHSH, Clauser, Horn, Shimony, and another person that I forgot the name right now. That is some function of A and B. Sorry, so some function of this probability distribution, and this thing needs to be less than 2. Less than or equal to 2.
To have this causal structure.
Yeah. So any probability distribution that is fitted, like is compatible with this causal explanation, has to satisfy this.
Yeah.
And in quantum mechanics, we get actually that this is 2 square root of 2 in the maximal violation.
Right. Yeah. So it violates this.
Yeah. So let me say it again. In principle, your theory could predict any kind of probability distribution here, right? And in quantum mechanics, we know how to compute this. But if you want to know somehow, if you want to have a causal explanation for your theory, then it has to satisfy this. And what it tells us when we see that quantum mechanics violates this, it tells us that this kind of story, where we imagine that there is a classical common cause that is responsible for the correlations between A and B, cannot be the case.
Right. Yeah. Cool. So, what does this tell us about reality, or what issues does this make us have to face with understanding quantum physics?
Right. Very good. So the question is, okay, if we can't have this kind of explanation, what explanation can we have?
Yeah.
Right. And like I should also say that there are several Bells. There's 2 theorems of Bell, and there's been many reformulations, and this is like my favorite way of thinking about it. But I'm sure your audience has heard about the local realism version of Bell.
Right.
And so what I want to say is that when we have this kind of constraint, that is, we call it a theory-independent constraint, right? Because it's about the space of possible theories. When we have such a constraint, it comes from assuming certain assumptions about your theories, and if you have another theory that violates, or even data, in our case we have actual data that violates this constraint. It means that the theory, whatever theory is that is able to explain this kind of correlations, has to violate some of the assumptions that we took to get to this constraint.
Right.
This is a subtle aspect of Bell's theorem that when I started getting into it, it was also really confusing, because it's in a course of quantum mechanics, but actually it's a theorem that is not about quantum mechanics in a way.
Right. Yeah.
And this thing about all possible theories, and it's a bit confusing, So that's just a thing. So one way that you can basically what you said, okay, this cannot be the story, right, in quantum mechanics. So some people say, okay, well, maybe the assumption that this guy is uncorrelated from this guy, which we motivated by special relativity, by appeal of special relativity, actually is not true. Maybe there is a causal influence between X and B.
Yeah.
And that's in a classical causal model with this kind of influence, we can violate the Bell inequalities. We can get all the way to the actual observed data violation. We can never go beyond that. But somehow this would be a coherent account of what's going on.
Right.
And this is the way, for example, Bohmian mechanics does it. So that in Bohmian mechanics you have the wave function. It guides the behavior of the particles, but the movement of one particle depends instantaneously on what another particle is doing.
Right. So it allows this causal
Right.
structure to happen.
So in particular, if I'm changing the orientation of the beam splitter over here, it can change the trajectory that the particle is taking on this other side.
Right.
Right. So this is a kind of explanation.
Yeah.
Then some people propose superdeterministic theories. That's where you have an influence, for example, from the correlation this way, say. This also allows to violate the Bell inequalities. And so you can have a superdeterministic theory. They're not particularly popular, but there are certain concrete examples or several proponents that propose this kind of modification. This tells you that even though you might be picking this, I don't know, you might be picking this one by flipping a coin, you might be picking this by looking at a pulsar and looking at what's the highest frequency light is coming at the moment in your apparatus. This thing, you bought it, I don't know, in Mexico, and you brought it to your lab in Vienna, and somehow still this guy can causally influence the outcomes of these two things. So it's a bit...
Yeah.
It's possible, but it's a really power... Like, if you have this, you can actually explain any kind of violations, any kind of correlations between A and B, if you have this kind of thing. So it's like a kind of cheap explanation in a way. You'd have to find ways to constrain it.
Right.
Another way to do it is somehow, when I wrote this equation here, it included implicitly, I didn't say it out loud, what we call the principle of the correlating explanation.
Okay.
And this what we kind of alluded to it before getting to the Bell inequalities, is that what it means for something to explain the correlation between two events is that if you condition on that something, the correlation disappears. It is called the Reichenbach's principle of the correlating explanation.
Right.
Meaning that if I want to know, if I have P of AB given lambda, this ends up being written as P of A given lambda, P of B given lambda, when the correlations disappear, which is what we see in here.
Right, when we're conditioning directly on this. Right, yeah.
And this is when the first time I heard about it, I was like, this doesn't sound too obvious to me, but it's a hallowed concept in the field of causal modeling, and it comes down to philosophy from a long time ago, what it means for something to explain a correlation.
Yeah.
And in quantum mechanics, like in the Copenhagen point of view, for example, we give up on this principle. So if we have a quantum state here, and we know the quantum state, it's not true that the probability of P of AB given xy can be written like this. What this thing is a joint measurement on rho. What this A and B is a joint measurement on rho, and this thing doesn't have this property that if you know rho, you don't get to the correlations.
Right, so the idea of this principle is that if A and B are correlated, there must be some explanation for that correlation, and if it's not, that one is kind of causing the other. So if they don't have this causal influence between them, then the explanation must be that there is something else that's causing them to be correlated.
Right.
And then if you condition on that thing, then A and B are not correlated because you've taken into account the source of correlation.
Yes, exactly.
And then you're saying that a Copenhagen-style interpretation of quantum mechanics says, okay, this principle doesn't hold, I can't get rid of these correlations between A and B by explaining them via this common cause.
Yes.
And
somehow it's really about what it means for something to explain a correlation.
Yeah.
Right. So in classical reasoning, to explain a correlation, it means that if you condition on that, the correlation disappears. Whereas in quantum mechanics, if you condition on the initial state, the correlation doesn't disappear.
Yeah.
And so if you want to say, this quantum state explains the correlation, we are losing this idea of a decorrelating explanation.
Right.
Yes.
Yeah.
And in Copenhagen, I mean, in a way, I think you and I are, being trained to do quantum mechanics, so we don't see this principle as natural, because in Copenhagen quantum mechanics it doesn't hold, but in classical mechanics it would hold.
Yeah. And then when you think about it,
we're kind of blind to
like,
this.
Yeah.
Right.
When you think about it, it's very intuitive that it needs an explanation for this correlation, and you can explain it that way.
Right. Yeah. So basically now, say that we we have the predictions of quantum mechanics,
Mm-hmm.
and there are predictions of the theory, but there are also experimental data.
Mm-hmm.
And we have a constraint on the kind of possible theories that can account for this data.
Mm-hmm.
And in particular, we have this thing that, for example, we know that because we see this, we need to modify this causal diagram in some way. So the different, if you see different interpretations of quantum mechanics as different theories of the world, then the different theories will have to violate one of the assumptions that we got here. And we already mentioned Bohmian mechanics, it violates the locality principle, like the no superluminal influence. We have superdeterministic theories, but in particular, I would say most interpretations of quantum mechanics that are not, most interpretations of quantum mechanics give up on this principle of a decorrelating explanation. And this is how Copenhagen interpretation, for example, fits with this version of Bell's theorem.
Right.
Yeah.
Cool. Great. Yeah, it's really nice that you can see all the different options with the
Right.
what arrows you draw or
Yeah.
onto the diagram. Cool. So shall we now kind of talk about the extended Wigner's friend and how this merges the Bell inequalities with Wigner's friend?
Right, okay, this is it.
So what is this extended Wigner's friend scenario that blends Wigner's friend with Bell inequalities?
Yeah, great. So the extended Wigner's friend scenario really is a merger of Wigner's friend and Bell inequalities, and the Bell setup. This, I think, was introduced by Charles Bruckner some time ago, where you imagine having a situation like before, where you have a friend with this own little apparatus in the box, and a super observer, Wigner, over inside the box, yes. And this is like the setup we had before, but now instead of having one, we have two of these setups in parallel. So we have another lab with another person in here, and with their own little apparatus, and another friend over here. Sorry, another super observer. And what makes it close to Bell is that these two labs, they get distributed a quantum system that is entangled. So the friend in here is receiving a quantum system and does a measurement on this system, and the friend over here is also receiving a system and does another measurement, and these systems that they receive are entangled. And there's a twist also on the Wigner's friend part of this, where we assume that there are two possible things that Wigner can do, the super observer. One scenario, they just open the box and see what their friend saw. And in the other scenario, we assume that they have full unitary control on what's happening inside the box. And what they do is that they revert the unitary evolution that corresponds to their measurement, and then perform a measurement directly on the system that the friend received.
Right, so are you saying they undo the friend's measurement of the system and then measure the system?
Yes. So as we saw before, we're thinking that in certain situations, it's appropriate for Wigner to assume that what's happening inside the box is a unitary evolution. Here we're assuming more than that. We're assuming that Wigner has such control over what's going on inside the box that he can undo this evolution. So apply the reverse, the adjoint unitary that describe the thing, which is something that you don't expect to actually be able to do, but in principle quantum mechanics doesn't forbid it.
Right.
It's a matter of control. I mean, it's thermodynamically difficult, you have to reverse all the things that happen inside the lab somehow, coherently, without like getting entangled yourself with the thing. But in principle it's possible.
Right.
And then once you do that, you are returned with the initial state of the system. Now the friend is unentangled. And now Wigner can perform a measurement on the system directly on a different basis. Or I should have said maybe that the two friends always perform measurements on the same basis. And only the two super observers they choose different measurements that they can do.
Right, so in terms of kind of qubit terminology, the friends always measure in, say, the Z basis. And the super observers can measure inside the labs in the Z or X bases, or measure the systems.
Right.
Yeah.
Yes. And in principle, if you want to, you can imagine even more different measurement settings. But yes, that's the idea.
Yeah.
Sure.
Cool.
And so the question now is, again, we have over here. Let's give names to these people. So here we have Alice that gets outcome A with her input X, like before, and similar over here we have Bob with his input Y. And inside we have Charlie and Debbie. These are the traditional names, but we can invent new names in principle. Charlie we assume gets the result C, and Debbie gets the result D. And now the question is, if I step back from quantum mechanics, like in Bell's theorem, we look at what kind of possible correlations A and B can have. So it's very similar to before. We have a probability distribution of A given B. Sorry, AB given XY.
Yeah.
Right?
Yeah.
And this is the data that is collected at the end of the experiment.
Yeah.
Because in the cases where Alice decides to rewind the friend, in particular, she will have to undo any trace of the outcome. So these two things are not available in general.
Yeah.
Nevertheless, even though in the quantum experiment we assume that this is a unitary evolution, nothing prevents us from also in principle assuming that this distribution is a marginal of an unseen probability distribution where we have Charlie and Debbie's outcomes as well. So we have A, P, B, C, D given X, Y.
Right. So is this, even if their measurements are reversed, we can consider this?
So the friend is inside the box. In principle, like several, the experiment can take arbitrarily long in a sense. So something is up. Maybe something is happening in the box. This is an assumption.
Right.
We assume that something definite happened inside the box. And if something is happening here and here and here and here, then in principle nothing prevents us from writing a joint probability distribution, even if we don't observe it.
Right.
If something is happening at every run, then it happens with some statistics of probabilities, and then we have this.
Yeah.
Right. And this assumption is part. This equation I wrote here is part of the assumption called absoluteness of observed events.
Right.
The idea is that the idea is that C and D are the value of an event seen by an observer, and we assume that this is a real thing that happened somehow. It doesn't depend on anything else. The friend wasn't there; they saw something, and that something has a definite value.
Right. Yeah. So if we have absoluteness of observed events, then C and D have definite values, and therefore we can write the probability distributions in this way. Right.
There's a second part of this assumption, is that we ask for this probability distribution to have a specific property, which is that when Alice decides to open the box, so say Alice opens, let's write it like this. So the probability of Alice seeing something when Alice opens the box, given the value of C, is equal to delta AC. Meaning that when Alice opens the box, with probability 1, she sees what Charlie has seen.
Right. Yeah. And the delta...
Delta is the Kronecker delta.
Saying that if A and C are they're the same outcome.
Yeah, this is a probability distribution. If you see this as a function of A, it's a probability distribution picked on the value of C.
Yeah, it's only non-zero when they're the same.
Yes, exactly.
Right. Yeah.
There's a similar assumption for Bob. So probability of B, Bob opens given B given D, then there's also P of BD.
So this assumption that A will see what C has seen if she looks in the box, and the same with B and D, is this part of the absoluteness of observed events assumption?
So in the original formulation of this theorem by Bong et al., these three equations were packaged together into the assumption absoluteness of observed events.
Right, I see. Yeah.
I think more recent work, both by me and other people, we make a distinction between these two assumptions. That here there is an assumption that something happens in the box.
Yeah.
And this is another assumption that when Alice opens, she sees exactly that thing.
Right.
They're kind of,
Yeah.
they come hand in hand in a way, but they're almost even independent.
Yeah. Yeah, I see what you're saying.
But it's certainly different. You could have this without this,
Yeah.
for sure.
Yeah.
And there are senses in which you could have this without this. But
Right.
but yeah, for the purpose of this work, we just assume this as a package, which is the natural assumption that, you know, when I enter the office in the morning, if I see my friend, then my friend was in there before I went in, and I see what he's seeing. It's very natural assumption.
Yeah.
And it's only a problem because of entanglement.
Yeah.
But this would be a very natural thing.
Yeah.
Okay. And then, this is a kind of shape. Again, I want to emphasize that we are not working within quantum mechanics now. We're just looking at a scenario, we're describing it. I mean, there's some quantum concepts, but the point is that this doesn't have to be an entangled pair. I'm just saying, there's my friend, there's my box, there's other things. And like before, we have a constraint. This is a constraint. This side here is a constraint on the kind of correlations I can expect to see between A and B, right? Because now I'm saying that the probability distribution of A and B is the marginal of a certain order distribution where there are these correlations inside. This is called the marginal problem. Again, people have studied this in statistics.
Right.
And maybe somebody has heard about monogamy of entanglement. It's this kind of class of like, if variables are correlated, if A is correlated to C, but it's also correlated to B, there are constraints on how strong these correlations can be between each other. And this is just a matter of probability distributions. It's got nothing to do with quantum mechanics.
Okay. Yeah.
Yeah. So there are these constraints. Then there's other two constraints. One is that, like before, the measurement input here does not influence D nor B, and similarly Y doesn't influence C and A. It's a locality assumption.
This is our constraint from special relativity again.
Again, yes, you can imagine taking these two things and bringing them really far apart. You can even imagine having this guy happening space-alike from this guy.
Right.
And so this should not influence this or this or this.
Yeah.
And similarly the other way around. This is an assumption of locality. And then we have assumption of no superdeterminism, meaning that there isn't a common cause correlating X and Y, say, or X and or C and D secretly in a way that we don't see.
Yeah.
Okay. So again, we have something like, so we have AOE, we have locality, and we have no superdeterminism. And these things together imply the local friendliness inequalities, they're called. Inequalities. Okay. Local friendliness refers to this package of assumptions. Or maybe only of these two, I don't remember now, but you know, it's local, it's friendly because you believe in your friends.
Right.
And so they're the local friendliness inequalities. And these are a set of inequalities that you derive, again, just by postulating a probability distribution and some constraints on it, motivated by metaphysical assumptions, you know, like there are no superluminal causation and stuff like that. And quantum mechanics violates these inequalities. So like in Bell, we have like a theory-independent constraint on a set of possible theories, and quantum mechanics violates this. In principle, I mean, we don't know, we never did this experiment with an actual friend.
Yeah.
Right? In the original paper, they did perform the experiment on a friend, but the friend was a photon. And we don't necessarily want to assign like a definite outcome to what a photon is doing because of the double slit experiment, nothing new there. But again, quantum mechanics doesn't tell us what is a friend, what is an observer. And so we can imagine making this quantum system progressively more complex to the point where, you know, it's just a very complicated piece of machinery, say, or in the limit, people have been studying the possibility of running this in a quantum computer with a simulated agent. that it ends up being a superposition. So you talk to the agent first and you convince yourself that he's a good friend, and then you make it do the experiment. But the point being that somehow, if quantum mechanics can be applied arbitrarily to arbitrarily large scales with arbitrary control, then it will violate the local friendliness inequalities, which means that if you believe that quantum mechanics applies in principle to all systems, then one of these three assumptions has to go.
Right. And as before, getting rid of no superdeterminism would be the superdeterminism interpretations.
Yeah.
Getting rid of locality in this sense would be kind of shifting to a Bohmian type view or something in that. Yeah, that's an example that relaxes this. And what would sacrificing absoluteness of observed events look like? What kind of interpretations?
Yeah, well, we don't know what it really means, but there are several candidates that have to take this, for example, because so these two assumptions are present in Bell's theorem as well. Locality in the specific sense is not presented in the diagram I drew before, but in the original version of Bell's theorem there was this assumption. So interpretations that violate no superdeterminism, they evade the conclusions of Bell's theorem the same way as they evade this theorem.
Right.
The locality people as well. So Bohmian mechanics resolves this paradox, this tension between this explanation and the predictions of quantum mechanics the same way as Bell's.
Yeah.
And all the interpretations, like Copenhagen interpretation, that evaded the Bell's theorem by saying, the word doesn't accord to Reichenbach's principle of common cause, or there's in the local realism formulation of Bell's theorem, there are no predetermined results. There's fundamental randomness. They are now forced to make the decision somehow again to give up one of these three principles.
Right.
And since they didn't give up this one in the first case and this one also, they are forced to give up this.
Right. So because this is different to the common cause Reichenbach's principle assumption, then proponents of interpretations that solved the Bell's theorem problem or explained the Bell inequality violations by relaxing this common cause assumption are now faced with a new problem by this inequality, and they now need to give an explanation for how they're going to solve this one, because the way they solve Bell's theorem or the Bell inequality violations, the way they explain them, isn't enough to also explain this.
Yeah, perfect. You said exactly right. That's the problem, and it's the thing that nobody saw coming, I think. One way I should probably mention, there's another way to get out of this conundrum is to say, no, quantum mechanics can never apply to observers, right? That somehow there is a limit to what systems can be treated unitarily, because we haven't done this with friends. But if you believe in principle extending unitarity to any system, then you have to somehow come on this side and somehow question what does it mean for violating these kind of assumptions.
Yeah, because deriving this was based on applying quantum theory universally. So you can also have an objective collapse theory, which says that at a certain point, say a certain size or mass or complexity, there is an irreversible collapse, the dynamics of quantum theory actually change, and that is how you get out of the
that's right.
problem.
Yeah, so there's a tension between these three assumptions and the universal applicability of quantum mechanics. It's not a tension between these three assumptions and data, like with Bell. Because in Bell we actually have the data that shows that Bell inequalities are violated in our world. This is a kind of inter-theoretic. We're still at the Gedanken experiment level of this. Yeah,
that's an interesting distinction because we've not done it yet. We don't have the data that then changes what it's actually telling us about reality, the fact that we have this inequality, because Bell's theorem, we've done the experiment, so that constrains the explanations in a way that this one hasn't been constrained yet.
Yes. Like we're not forced by reality to confront these assumptions, but we are forced by quantum mechanics to confront these assumptions. And because quantum mechanics is our best theory of the world, we want, at least in the foundations community, we want to understand different possible ways of thinking about what quantum mechanics tells us about the world. And one of the things it tells us is that these two things cannot hold.
Yeah, right. And what would an Everettian type viewpoint say about this?
Yes.
I guess it's in the absoluteness of observed events.
Right, yes, it's on this side, yes. And I should mention also that this absoluteness of observed events was in the background of the derivation of Bell's inequalities as well. We assume that Alice and Bob, they do their experiment and they get a definite result, and they really get it in that moment, in that space. There is like a joint probability distribution between the observations of Alice and Bob and their setups at the moment of their measurements. Somehow you don't have to wait for them to meet, say, in the future to actually have that correlation. We assume that we can write this right at the moment they get the measurement and not like sometime later.
Right.
And this is true in Bell and it's true here. It's just that here, so this theorem is like, these assumptions are strictly weaker than Bell's theory, so it just like highlights the fact that there is this. Okay. So the way in Everett you would do it, clearly it would be something about giving up this assumption. Yeah, I mean, so the Everettian story in this kind of experiment obviously would be that inside the box, the measurement causes sort of branching contained inside the box, where there are two friends now, they've seen two different things. So there are two friends here and there are two friends here, there are four friends inside the boxes, and it's not quite clear what this object should mean, because how can you conditionalize on both values? Somehow, like, this kind of probability distribution is about classical variables.
Yeah.
Now inside here you have this complicated quantum state.
Yeah.
It's not clear what this would even mean.
Right.
To write something like this. So basically, you jump out to the theorem immediately at this stage.
Right.
Same for Bell's inequalities, where we have A and B over here with X and Y, and we have these influences like this. Oh, sorry.
Yeah.
We have these influences like this, and we have in an Everettian point of view, we have two Alices and two Bobs, so it's not even clear what it would mean to start writing P of AB given XY, because there isn't one. A only happens. Yeah. So the Bell's, like the whole framework of Bell's theorem and this theorem, and in general the device independent theorems that exist, other theorems of this form, they all start with the idea that outcomes are labeled by classical variables that can take only one of the possible variables. Whereas in Everettian quantum mechanics we have really this complicated worldview where the outcomes, they all happen, right? Or the outcome is represented by, depending on how you want to slice Everettian interpretation, you have like the outcome is the descriptor of the atom, or it's the correlation between the variables and stuff like that. It's more complicated, it's richer structured, and so you immediately fall out of the paradigm of even talking about these things in a way.
Right. So in a similar way to how the Bohmian explanation for Bell's theorem is the same as its explanation for this, and superdeterminism, Everettian also has this kind of common explanation for why it would violate both.
That's right.
How it can explain both inequalities.
Yeah, that's absolutely right, yeah.
But the kind of new problem it poses compared to Bell's theorem is saying that using this Reichenbach's principle is not enough to explain this one.
Yes,
and
exactly.
so that's what someone that doesn't subscribe to one of those theories then needs to explain how they're going to explain this, because they sacrificing that principle, which is what they did to explain Bell's theorem, and the data we have for that isn't enough to now explain this.
Yeah, that's exactly right. So the way I like to say it is that there are these Copenhagen and like neo-Copenhagen interpretations, where you have this notion of quantum common cause that solves Bell's paradox. Here, these interpretations are kind of dragged into taking a position on what is a system, what is an observer, what is an observer, what does it mean for something to happen relative to an observer in a superposition. So it drags like relational quantum mechanics, QBism, even neo-Copenhagen interpretations. There's like this idea like quantum mechanics doesn't need an interpretation because it's about data, about the real world. These interpretations now are forced to kind of talk about this. And I mean, QBism and relational quantum mechanics already had a sort of notion of relative facts, of facts, like it's possible that Wigner describes the friend in superposition, while still believing that the friend saw something. Like they already kind of entered this territory, but now we're really like confronted with making concrete choices of what it means for these things to happen. So, for example, one way out of this thing is that when Alice opens the box, actually she doesn't necessarily see what the friend saw. She sees either disturbs the friend deeply, or actually she kind of live in parallel worlds where she saw something and the friend saw something different. Or we have to start saying, okay, maybe we cannot write this probability distribution, but then we still have to say, but what happens to the friend? And this is an ongoing discussion, I think, in the community, in these interpretations, to try to figure out what to do. So what I was saying is that before this thought experiment and these theorems, interpretations like QBism and relational quantum mechanics had some story of the form Wigner and friend give different accounts of what's happening in the experiment because different things happen to them, or they know different things about what's going on. And that sounds like a okay, satisfying story until this theorem really forces you to mean, but what do you mean by this they describe in different ways? Like, what is, in your interpretation, what is happening really in the world? Like, does he actually see something and Wigner is just ignorant? So can we write this probability distribution? But then if we can write this probability distribution, can we assume actually that when Alice opens the box, she sees what Bob saw? And it's been a headache trying to figure out this, and it's fantastic actually to think about this because we had this story for many years, and now we have a concrete result that really forces us to sharpen our intuitions.
Yeah, cool. And you mentioned earlier that one of the things you've been thinking about in your recent work is kind of drawing a distinction between these elements of the absoluteness of observed events assumption. So is that kind of relating to what you were just saying about trying to define where these interpretations now need to relax something from there? Yeah.
So here we're moving in like the forefront of research in relational quantum mechanics. It's a discussion probably ongoing at the moment. But somehow, so in relational quantum mechanics, we have this idea that there are facts. So when two systems interact, somehow, because I need to get an influence from you, you need to like tell me what your variables are somehow. So that if you're in a superposition, but I interact with you, suddenly I get like a kick, and the kick is concrete value of a variable. And we call this a relative fact because a system outside our interaction would not assign a relative variable, like a definite variable to the outcome. They would assign us entangled, which is precisely what's going on over here. So Charlie has to see the outcome. So for him, there is a definite outcome. It's a fact relative to the friend. For Wigner, who's outside, he's describing the whole thing in a superposed in an entangled state between Charlie and the apparatus. And we had this notion for a while of there's like the collection of relative facts. People also working in other interpretations have this notion of perspectives, the perspective from a friend, from a Wigner. And so the question is, what can you do with the different perspectives? Can you imagine that the different perspectives somehow coexist in the same world? If you do, what's preventing you from writing a probability distribution of this form? And somehow now there's a recent work by a philosopher, I forget the name right now. He introduced this notion of tame relationality and feral relationality. So tame relationality is this idea that there's the collection of relative facts, and basically every fact is labeled by the systems that are what is relative to. Right, so there is a relative fact of the outcome of this that is relative to Charlie, but it's relative to Charlie, but it exists. Right, and there's somehow this whatever Alice's measurement input, I don't know, it's a fact relative to Alice, right? But it exists, and they're all there. And this is tame relationality in the sense they live with each other. But tame relationality comes if you believe that there is such a thing, then you are in trouble because then you have to modify this, and somehow when Alice opens the box, all of a sudden, what she sees is not necessarily what Charlie saw anymore. And this is weird. So tame relationality actually doesn't really work. If you want tame relationality, then you have to give up on locality or on superdeterminism.
I see,
Because if you want to keep this and this, exactly. Then you have to give up on these things. But then, what is relative about these things in the end, right? In the end, it's just I didn't have to tell you about this, I could have just written this, and then you'll have to give up on this. So it's not really relational. If you don't have this, you have this feral relationality somehow that we don't really know what it means. If we can't write this, so if we don't want to give this up, or no, sorry. If we can't write this somehow, then what does it mean? Like, there's no answer really still about what's happening inside the box. So maybe somebody will say, okay, well, if I don't open the box and I do the interference experiment, it's just not an empirical. There's nothing about what Charlie saw, because nothing in the universe will ever know what Charlie did. Maybe Charlie did see something for a while, but because I do the interference experiment, I completely give up on ever knowing forever in the whole history of the universe what happened. It's like when you do the double slit experiment and you get the screen, you would just never know where the particle went. So somehow it doesn't even make sense to ask the question, where did the particle go?
Right.
But in this case, we have a guy in here, or a woman, and they're stuck in here, and you would want to see that something happens in it. But some people are satisfied with just saying, okay, well, we just don't ask the question. If we want to ask the question, we open the box. If we don't open the box, then we're not asking the question, right? Or there is something more like, okay, maybe there's a relation between Charlie's and thing, and the relation between Charlie and his outcome depends on what Alice did to him, and then, but maybe Alice also is inside another context, so her thing also depends on something else. Is another way that I haven't explored personally too deeply, so I cannot say anything super smart about it, but it also has this kind of, in this case, while in the first case, it looked like there was less reality, somehow here the reality is like super complicated network or relationship that never stops, because all facts depend on other facts. But if no fact stands on its own, but only stands in relation with other things, it just keeps growing, this confusing thing. Maybe it can be made sense of, I don't know. Philosophers are working on it.
Is there a name for that kind of thing? Or?
It's also the feral, it's like, it's part of this feral notion of relationality that we still have to explore. Yeah.
Cool. Well, I think we've done quite a nice summary of the thought experiment and the different options for trying to explain what this result is telling us, and also bringing us right up to the forefront of current research and your own research and what people are doing right now on trying to understand this. So before we kind of wrap up, is there anything else that you think is worth mentioning about this, or about the context of research on this topic?
Yeah, I think so. I believe that this result is possibly the most exciting result in foundations for me at the moment, and it's been really, because it forced us to go into this box somehow, it really forced us to re-question certain interpretations that we thought were kind of standing on their own, and actually look at them better, and to see that actually they were not that immune, they were not that clear what they were saying. And it's quite amazing to have a little mathematical proof that shows you that a really complicated story just can't hold. It's quite fascinating. And this is this field that my colleague Gary Cavalcanti calls experimental metaphysics. That is also a name that Shimoni gave to this field, which is Bell inequality, the Cocker-Specker theorem, and this theorem are all examples of experimental metaphysics where you have some sort of quantitative mathematical theorem that constrains the possible theories of the world. And the theories are, in a sense, metaphysical in the sense that we rely on assumptions that they cannot necessarily be directly observed. Like, this locality thing is designed in a way that you cannot actually go and check that if the world is according to this, but you know that it cannot be according to the three things together, because that has a observable consequence.
Right.
I think it's like really exciting way of doing science. I mean, this is obviously it's part of the influence of Bell's theorem that kind of showed this kind of thing. And besides, so I am interested in this from a foundations point of view. I'm actually interested in understanding what are the ways we can think about the quantum world. But this kind of stuff is used also for developing technologies. So theories like things like quantum key distribution, various encryption protocols and stuff like that, they also have they call device-independent versions, where you prove that you can prove similar theorems to Bell's theorem, where you see that if some kind of correlation is violated, then your quantum computer has a resource that, say for example, you cannot spy on a certain signal, because by this kind of device theory-independent arguments, you know that if somebody was looking at it, then you couldn't see what you're seeing. And it's kind of amazing that you can have a tool that was developed for super, abstract idea, and actually can go and be super concrete about like verifying encryption protocols and stuff like that. It's quite amazing actually. You can do both things with this kind of work.
Yeah, that's cool. And I guess in those situations they also have some kind of general principles that they're assuming are holding for these kind of security results to hold.
That's right. You have several like metaphysical assumptions that are, as natural as locality and superdeterminism, and that we, for all practical purposes, don't question, and they derive bounds on the things that you can do or not do with those things.
Yeah. Cool.
Yeah,
great. Well, thank you for joining us today and for the nice explanation of this thought experiment, which is very subtle and confusing, I think. So I think you did a really good job of kind of laying out the different aspects of it. It's definitely made a lot more sense to me than it ever has before. So
that's great. I've been thinking about it a lot more recently, so it's kind of fresh in my mind. That's good. Maybe we can recommend some papers that are kind of overviews of these things that could be useful.
Put them in the video description.
For people who want to learn more, because it's the mathematics, it's confusing. There's a lot of words and a lot of concepts, but the mathematics in the end are quite straightforward. And I feel it's a good thing for everybody that works with quantum stuff to be aware of these kind of results. Not necessarily from the foundation's point of view, but also from the foundation's point of view, to know what we're working with.
Yeah, cool, great. And maybe when you've made progress on more of these problems, we can have you back again to tell us what you've discovered.
All right, with pleasure,
So thanks for joining us, and thank you all for joining us today. And please join us next time for more Quantum Foundations discussions. Bye. Snapshots of the board, and I'll take a picture before we...
I never normalize mistakes, I hope people don't mind. You can see it.
Yeah.
You can see it. It's very small, and because I've been presenting the poster on this, so like it's really really uploaded in my head.
I'm also just thinking maybe it's better if we switch places, because so then you can kind of...
Is it better? Because I'm gonna be writing like this.
Okay, yeah, sorry.
No?
Yeah, white blackboard.
Yeah.
What's your group called?
We are in the Quantum Information Structure of Space-Time group, led by Marius Christodoulou.
Yeah, so this is
very advanced technology.